Hello, Hubble huggers, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and we have another really interesting hangout planned for you this week. Astronomers using NASA's Hubble Space Telescope and the European Southern Observatory's Very Large Telescope in Chile have discovered a never-before-seen moving features within a dusty disk surrounding the young, nearby star known as AU Microscopy, or affectionately known as AU MIC. And we're going to be talking today about some of the findings of these observations with the astronomers who made them. But before I get started, let me let you know that we want your comments and your questions throughout the Hangout. And there's several ways you can let us know how to do that. The easiest way is to use the Q&A app. There's a little button on the lower left-hand corner of your screen called Q&A. You push that, and you can ask a question. I've already seen a whole bunch of them right here, and I'm going to be getting to them as we go along. And feel free to also do your comments as well. We're also monitoring the Hubble Hangout hashtag, just Hubble Hangout, not the hashtag part, and on Twitter. So I'm looking at that. I won't be live tweeting this particular one, but we will be looking for that Hangout. Also on the G Plus event page. If you want to leave comments there's plenty of ways to do it. We hope you'll ask our guests lots of questions. But before I get started with my introductions, let me welcome my colleague and friend, Dr. Carol Christian. She is the
Hello.
Hi, Carol. She's the outreach scientist for the Hubble Space Telescope. How are you doing?
I'm doing well.
Yeah, you're doing really good. So
I escaped the floods of the South, so I
wanted to ask you about that. I know you were heading that way. I heard that.
Yeah. Anyway, we made it.
That's great. Well, welcome. It's good to have you back, and looking forward to a good conversation here today. With me today is Dr. Glenn Schneider. He's an astronomer at the University of Arizona. Also joining me is Dr. Carol Grady. She is an astronomer with Eureka Scientific. Sorry, couldn't read my writing there for a minute.
Eureka Scientific.
She's based at Goddard. Welcome, Carol. It's good to have you. Also joining me is Anne-Marie Lagrange. She's a researcher, and I'm going to let her tell you from where in just a minute. And also joining me is Dr. Anthony Boccaletti. He's from Paris Observatory, also an astronomer. Welcome, folks. I'm glad you guys could all join us.
He's from Grenoble.
Exactly, Grenoble.
Grenoble.
Yeah, so you can see why I wasn't going to do that, right, folks? If I had done that, you would have been like, "What's he saying? Oh my God, he really butchered that." So okay, so our team here today has used the Hubble telescope and another observatory known as Sphere as part of the Very Large Telescope that runs by the European Southern Observatory in Chile to look at a nearby star known as AU MIC, and it is about 32 light years in the constellation Microscopium. And I'd like to get, I guess, who can give us some background on this? Glenn, would that be something I could get you to give us some background on the star system itself? What kind of star is it, and things like that?
Sure, happy to. Yeah. Yeah. So AU MIC is a relatively young star. It's between about 10 and 20 million years old. It's visible in the southern hemisphere. It's about 32 light years away. It's a very low-mass star, what we call an M spectral type star. It's about 30% the mass of the Sun or so.
Oh, wow, really? So it's pretty small.
It is. It's red, it's cool. It's about 3,500 degrees Kelvin, more or less, surface temperature. And it is a very active star, very chromospherically active. It has lots of flaring events and rather violent events, what we call mass ejections from the surface, chromosphere.
Now our sun actually does that too, right? I mean,
it does. And it absolutely does, but not with the frequency and not with the energy relative to the size and energy of an M star. So these are some, I won't say catastrophic, but they're very energetic events for a small star.
So for those of you who don't know, the chromosphere is this sort of layer of a solar atmosphere, or stellar atmosphere, I guess, in this sense. It's above what's called the photosphere, which is what, on our sun at least, is where things like sunspots or where those are seen in the optical wavelengths. But then it's a layer right above that, a little bit higher up, but it's in between that and the corona. Am I right?
That's exactly right.
Okay, so it's this very special region of AU MIC that you were looking at.
Well, it's not that we were looking at the region. It's just the chromospheric activity is a marker of the activity in the star itself. So we know
I see.
It's a very active star.
I see. It's just a characteristic of its activity. I see. And Wow, that's interesting. I'd like to talk more about that in a little bit. But so this star's pretty close by, and what was the motivation for looking at this particular system?
So AUMIC is actually a member of the Beta Pictoris moving group. There's an association of stars in the southern hemisphere that are of common origin in terms of where and when they formed. Beta Pictoris, of course, is famous for its very large and well-known disk that was discovered in 1985. AUMIC is sort of its baby cousin, you may want to say. It's a smaller disk, but it's a very bright one and very massive one. The disk was first seen in 2003, I think, by Paul Callis. I may be wrong about that. I think it was identified on the ground, actually. I apologize, by Michael Liu. But the disk has been known for some time. We observed it last year. Excuse me, we reported it last year, but we observed it in 2010 and 2011 with Hubble, and Anthony now has done observations with Sphere that we'll talk about. So it was the follow-up that Anthony did, then going back and looking at our observations again, that really formed the collaboration between what we were doing with the Sphere group. The Hubble data that we took, and I don't want to get too much into the data here, they were taken in two epochs fairly close together in time, and we treated them as one coherent data set. But it's actually very interesting when you start breaking apart sort of the time resolution, especially the time baseline that Sphere gave us, or as Anthony did. They went back in 2014, looking at it many years, 3 to 4 years later. So we're able to see.
Yeah, I want to get to the specifics of the observations here in just a little bit, but before I do, I kind of want to set the stage here scientifically. So we know a little bit about this star. It's very active, 30% the size of our sun, relatively close by at 30 or so light years away. But it has this thing around it called a debris disk, and it's this. And I think astronomers and Carol, maybe I can, or Carol Grady, maybe I can get you to comment on this a little bit.
Okay.
Most astronomers, I think, are thinking that these exoplanets that we're observing with other things like Kepler and others and other instruments are sort of condensing or coalescing out of these debris disks. Is that right?
Well, debris disks are actually the smaller dust grain component of what are probably planetesimal belts. That you can observe using ALMA, and
ALMA is a radio telescope or a large multimeter array. Yes, it's also in South America. So
and for the debris disks, we think that by the time you get to, you start off initially with a disk that is gas and dust rich. That looks initially something like the composition of the molecular cloud that it formed out of. And then over time, planetesimals, cometesimals start to grow in these disks. And you can, under favorable conditions, you can form Jovian mass planets. Now, we have not detected a planet yet in this disk.
So debris disks, then, am I hearing you right when you say that debris disks are these sort of things that come along much later in the planetary formation process?
Well, after the Jovian mass planets form, but they are a going concern while terrestrial mass planets may still be forming.
Okay, so the gas part of these early disks then would come and sort of coalesce into these gas giants, you're saying, right?
Yeah. By the time, however, that we're looking at something like AUMIC, this system has lost the vast majority of its gas. There are only upper limits on gas detections within the disk. And what we do see, with ALMA and other millimeter telescopes, you see millimeter to centimeter size chunks of gravel. What we would see with Hubble is actually the smaller dust particles, sort of smoke particle sized stuff.
So Tony, let me just jump in. Oh, sorry.
Go ahead.
Yeah, let me just jump in real quick, and just a simple discrimination is debris disks are basically material that's second generation material. It's not the original stuff that was like in the interstellar medium that the protoplanetary disks grew from. So the dust and small particles we're seeing are a result of collisions within that disk. It can be dynamical, small particles, planetesimals, crashing into other things and then making smaller dust grains that get thrown out. So we're seeing a later evolutionary stage. It's not the protoplanetary initial stage. It's a little bit later on after the planets are formed.
Okay, but Carol, as you were saying, that the stage with which a lot of these big planets, like gas giants, that would form, by this time you're saying has probably already happened, right?
It's already happened because you can only form something that has a lot of gas if you have gas for it to form from.
Okay, all right, thank you. So we're looking at something a little bit further along. We haven't seen planets, as you're careful to point out, around AUMIC, or at least gas giants yet. And there's still a possibility that there are terrestrial planets forming from this debris disk. Amy, let me get you in on this. Tell us a little bit about your observations with SPHERE. First of all, tell us what SPHERE is. It's been and what it can do, and what was your interest here in using it on this particular system?
So yeah, SPHERE is an instrument that was put at the VLT in May, which we started the development, in fact, 12 years ago, about 12 years ago, I think, in 2002 or something. So it's one of this system with a very high contrast imaging system, which combine adaptive optics, but very extreme adaptive optics, which is able to correct the light from the star very well, almost at the limit of the diffraction, in order for the second stage of the instrument to work very well, which is the coronagraph. And the coronagraph is here to take out the light from the star, in fact, and to be able to see or to detect disks or planets behind.
Okay, so SPHERE is an acronym, as all things are in astronomy, which stands for Spectropolarimetric High Contrast Exoplanet Research Instrument. And so the name implies polarimetric. Sorry, it's got a polarimeter on it, which means it only looks at polarized light. Am I right? And it's got a spectrometer on it somewhere.
Well, in fact, it does all of this. It does imaging, it does spectroscopy, and it does polarimetry, both in the infrared and the visible.
And on top of that, you're saying it's got a coronagraph which has an occulter on it, which blocks out the light from the star, which we've talked about many times in the Hangouts before. That's important because the light from the star is so bright that we need to see something billions of times fainter from the star that it's around. Am I correct?
Yeah. Correct.
Okay, so you block out the light from the star, and then why is it important to? Well, I'm trying to decide if I want to talk about polarized light and why that's important. But let's go ahead and say, in order to see these debris disks, we need to see the polarized light, or see it in a polarized filter.
Not necessarily. The images we got with SPHERE are just unpolarized light in that case.
Okay, so the spectral part, the part that does the imaging and the spectrum with the spectrometer, that's the part you're using?
It's an imager, in fact. Well, SPHERE has three instruments. Okay. One of them is the imager in the infrared. One of them is the spectrograph in the infrared.
Oh, okay, thank you for. Okay, I get it now. So you blocked out the light. You can both image this disk as well as measure its spectrum. So and Elena has something up here now, which I think. Are these the observations from SPHERE, or no? They're Hubble. These are Hubble.
It's a combination. So 2010, 2011, it says HST STIS, and then the last one is from SPHERE. And so that's wherein lies the interesting part.
Okay, good. Well, let's talk about that. But I haven't asked Anne. I'm going to get Anne-Marie on this a little bit. Can you tell us about your role in the project, Anne-Marie, and maybe give us some of the things that you were hoping to see from this system?
Yeah. Well, my role in SPHERE was I was the leader of the project at its very beginning, when we proposed the project to ISO, which was a kind of a crazy idea at this time.
Really? Okay.
Now, in this project specifically, I took part of the observations and also to the reduction as well of the data. Okay, I'm mainly interested in looking for disks and also for exoplanets.
So what came first, the Hubble observations or the SPHERE observations, or were they both done concurrently?
The Hubble observations were done in 2010 and 2011, and SPHERE followed in 2014.
Okay.
Hence the label on the graphic.
I'm talking about it and asking. Okay, so thank you, Carol. All right, so let's talk about what you found. So you looked at the you used these two instruments, Hubble way before Sphere, and you looked at this debris disk, and you found something that was surprising. Why don't we start with? Go ahead, Carol. Do you want to? Carol Grady, do you want to talk about the what you found, and then I'll have the sphere guys talk about what they found as well.
Since AUMIC was first observed from space, it has been known that the disk is not the same on both sides of the star. On one side of the star, the disk is relatively featureless, although there is a bit of a warp. On the other side of the star, there are little blobby features. And this is what we found were moving.
So these little bright blobs that we're seeing on the right and left here and the center part, that's the occulted star, right?
Yes.
Okay. So you blocked out the light from the star, and you see these blobs. What you don't see in other debris disks?
Well, other debris disks have shown structure, but nothing moving. We have 2 epochs of Beta Pictoris imagery, and nothing moved. Absolutely nothing moved. And we've been analyzing some additional second epoch observations, and thus far we have seen no sign of any movement.
Okay, and Anthony Boccoletti, you looked at this with Sphere a little bit later, and when I look at this, I see more blobs than in the top 2 frames. Is that just because it's done a little bit later in time, or is this thing evolving? What's going on there?
Well, in fact, Sphere has a little better angular resolution than the HST, even if it is observing at longer wavelength.
No way.
Bigger,
better than HST?
Sorry.
No, I don't.
Sorry for that.
It's on a much bigger telescope. Hubble's a little telescope.
Okay.
All
right. So Sphere's better than Hubble. Go on.
No. I just said the angular resolution of this image is a little bit better than the one from STIS. That's it.
Okay, so we're not necessarily seeing any evolution going on here between these frames as far as the features themselves, then, am I right?
Well, we do see some evolution. And so, in fact, when we observed the star in 2014 with Sphere, we were surprised to see that many structures that we haven't seen before, not as much clearly as this. I mean, even if in the former HST image we have seen some blob, as Carol's just said, they were not as obvious in the Sphere image. But it's also a lot about the data reduction that we are doing on the Sphere data. Just because it improves a lot the contrast naturally at the stage of the data reduction, that we have seen this feature very well in the Sphere images. And at this time, when we saw that, we thought it was already a very good surprise, and then we started to contact Glenn and Carol and others to see if we can learn more with older images from the HST. And this is where we found that, in fact, all the features that we have seen were already present in the HST images. And then we were able to measure a motion.
So you got a motion from that. And what did you, how fast are they moving?
They're moving very fast, in fact, between 4 and 10, 11 kilometers per second. It depends on which one you're talking about, but what is surprising is that the one which is the closest, well, apparently closer to the star, is moving slower than the one which is the most distant to the star. So okay. There is a kind of dispersion of the velocity of the feature, okay, so depending on their projection, on their distance, the projected distance to the star.
Okay, so Carol Grady, I'm reading your quote here from the press release. Because nothing like this has been observed or predicted in theory, we can only hypothesize when it comes to what we are seeing and how it came about. What about, you can't even hypothesize, what are you hypothesizing, I guess is what I should say.
Anthony should probably address this. In the Nature paper, we considered a number of different mechanisms, starting with the simplest one, which would be that we're seeing something orbiting in the disk. Unfortunately, the features go out beyond the known location of the planetesimal ring, which is at minus 40 AU, plus or minus a few AU. And we didn't see a characteristic, say an outward motion and then a stall and then a turnaround, which would be what you would expect to see for something in Keplerian orbit, orbiting in the planetesimal ring. So some of these things go out beyond the planetesimal ring. The other, we've actually considered a whole bunch of mechanisms, including a link to stellar activity, and that what we may be seeing something where a Jovian mass planet closer in plays a role. But Anthony can probably speak to that.
All right, Anthony, go ahead. Do you have anything to add to that?
Yeah, well, it's very speculative, I should say, first, because we have no idea of what is going on. We do see these things, this feature moving very fast, and we have no real interpretation of this motion, especially because the star is the disk is seen by the edge, so you only see the thickness of the disk, and you are not able to determine which is the physical distance of this feature and which is the real velocity of the feature. You only measure the projected velocity and the projected separation to the star.
Okay.
So with that, you have to deconvolve and guess where the features are in the disk, which is not possible at the moment. So that's one of the problematic in this in the interpretation of the feature.
Okay, I think you sent us a nice animation that sort of outlines some of the things that you think are going on with the dynamics of these observations. I'll let Elena get that put up when she gets it. But as she's doing that, I want to go back to this thing about what was it called? A planetesimal ring? What's it? Yeah. What is that?
Well, it's an analog. It's a younger version of our Edgeworth-Kuiper belt.
Oh, okay. So,
and
you're saying that these blobs are well beyond that. They're well past that.
Some of the blobs are clearly going past this system's version of a Kuiper belt.
I see. Okay.
They just seem to keep on motoring on out.
Okay, so here we have an animation that Anthony put together for us, or not for us, but for to take an idea, to take a look at what's going on here with the dynamics of the system. So here you have. Well, I'll let you go, Anthony. Why don't you explain to us?
Okay, you start from the beginning. So just some basic facts about the star. So this is the sphere image where we have seen the images, which are indicated by blue arrows here. Okay, so we have 5 features. Depending on the data reduction, you can see them more or less clearly. So this is the second sphere image here, the same epoch. And then compared to the Hubble images at the top in 2010 and 2011, reprocessed to detect this 5 feature, which is not already obvious in the images. This is just a circle to indicate the orbit of Neptune, to just put a scale.
Ah, okay, that's good, yeah. Okay.
And so we note the feature A, B, C, D, E in that case. Okay. And then from that images, we are measuring the position very accurately of the feature, because they are seen as very particular peak in the cut in the cross section of the disk. And if you draw a line from 2010 from the first feature to 2014, you can see that it's clear the motion is really obvious in this case. And in fact, the feature B has already moved in between 2010 and 2011. It's already visible in the images of Hubble.
And that's how you got the speeds.
Yeah. So when we do the same thing, but carefully for all the 3 epochs, 2010, 11, and 14, measure very accurately the shape. And this is the speed that I just mentioned before. Maybe you can stop here if you just go back on the previous slide, because it goes too fast. So yeah, so this 5 feature, A, B, C, D, E, we have measured the projected speed and projected separation, and compared them to, as Carol said, to Keplerian motion, depending on the eccentricity of the orbit. And what we see here is for different assumption on the mass of the star, which is we took it very conservative here, between 0.4 and 0.8 solar mass. Maybe it's rather 0.5 or 0.6. We don't know exactly. But we see that the feature D and E and maybe also C are clearly above this line, above the solid line, which gives
Which solid line though? The purple one?
Yeah, the three colors, in fact, the colors correspond to the mass of the star. So the solid lines, the three of them, the three features C, D, E are above this line, which means that they are faster than the escape velocity of a system.
Okay. And it goes back to what Glenn was saying about how small the star is. So okay, I got it.
Yeah. So it depends on the mass of the star, of course. But clearly these three features are going faster than the escape velocity, so they are going away from the system.
All right. So Anne-Marie, let me ask you a question about this instrument real quick. You said you were a part of the team, the head of the team that helped develop this thing. Are these the kinds of observations that you were hoping to get from this? And are you satisfied with? I mean, these look to me to be pretty high resolution results.
Yeah, we were actually Sphere was built especially to find planets, exoplanets, but we also designed it so as to be able to detect disks such as this one, or like the Beta Pictoris one. And so okay. Yes, and it works quite well with detecting a disk. We have also detected one new disk that will be appearing tomorrow on AstroPH. So it has been quite successful to detect such type of debris disk.
Oh, good. Well, I've got more questions about the future of this instrument in a little bit, but I think I should let Anthony finish with the animation here because we caught him. I stopped him, but yeah, I want to ask you more about the future of Sphere. All right, go ahead, Anthony. You want to finish up the animation?
Yeah, you could go to the last slide, which is just a summary, and you have a color image. So yeah, we don't know exactly what mechanism is producing the structures, and as Glenn already mentioned, the star is very active, so we suspect that this activity is involved somehow in the generation of this feature, but we don't know exactly how.
Well, that makes sense, though, doesn't it? I mean, in the sun, at least, that activity, like mass ejections, are a magnetic event on the sun, at least. I would imagine it's something similar to that going on here, wouldn't you? Would that make sense? That the activity is somehow?
Yeah, but sorry. Go ahead,
Anne-Marie, go ahead.
Yeah. Well, the star is, as Glenn said earlier, is much less massive than the sun, and its activity is not exactly the same as the sun. On the sun, you have plenty of small spots, dark spots, and facula, whereas on Ionic, when we observe it in spectroscopy, we see that there is mostly one big spot. So the type of activity is very different from the sun one.
Oh, I'd love to see that. That'd be cool.
One thing which is very puzzling with with finding any origin to the disk, to these features, is the fact that we see them only on one side of the disk.
Right.
And this is really a mystery.
Yeah, I was gonna ask about that. And can you also comment about the geometry, because some of this stuff is like rotating too, right? I mean, isn't it in orbit? I mean, it's going outward, but
no. Apparently, they are not orbiting. They are really
just
moving
going straight out.
Well, we don't know exactly in which direction. Is it perpendicular to the line of sight, or some of them are going towards us? Maybe we don't know exactly. But what is puzzling is really the fact that they are on one side of the disk. And if it were only the activity of the star, it will be in any direction, not just in one direction.
That's weird. I mean, I think this illustration is really nice because, I mean, the other side, you can, it's really obvious this stuff isn't there. So
yeah, but wait a minute. You don't know enough about the activity of the star yet to really know for sure that maybe it could be all on one side, right? I mean, who knows?
Yeah, I'm just saying it doesn't look like there's anything on the other side.
Yeah.
Right. Well, in terms of activity on the star, X-ray activity, this thing the star produced a massive flare. that released about 10 to the 34 ergs. It was a long-duration event. It was observed in 1992 and went on for several days. The shape of the flare, light curve, prompted suggestions at that point that we had just seen a coronal mass ejection.
Wow. So I'm sorry, but that is comparable to the sun then, because our mass ejections.
Wow.
It is.
That's
This is
amazing.
orders of magnitude more massive than solar.
What are
Then
they?
even
I guess
things like
you're right. They're about
Carrington
10 to the
events on
30.
sun.
I guess the ones here are like 10 to the 30, 10 to the 31. So
Yeah.
you're right. I guess they
This
are.
is orders of magnitude more active.
Yeah, and as Anne-Marie was saying, there's this one big, apparently active region, supposedly, that may be responsible for this. So that is hugely interesting. I would love to see more of that. Are these debris disks? I don't know how to. I guess they can't be really magnetic, can they? Because that's all just dust, can it? So the magnetic fields, I guess, aren't going to play a role. I guess is where I'm
Well,
going.
we don't know the magnetic field topology in the disk. We also don't know the magnetic field topology at the star very well either.
Okay, all right.
So,
So there's a lot to learn about AUMIC. Okay, Glenn, did you have a comment? You looked like you were getting ready to say something, or was that just you smiling at me? Okay.
You're sorry. You're talking to me? Just sorry.
Yeah, did you have a comment, or
Yeah, I just also wanted to say, with regard to the activity that Carol has spoken to, also put it in context of the energy relative to AUMIC itself, which of course is a much smaller star than the Sun is.
I know that makes it really remarkable, in my opinion, that a smaller star would have such orders of magnitude more powerful eruption.
So the other two things that I simply wanted to comment on here just for a moment is the other thing that's intriguing. Of course, you know, we are, as Anthony's been saying, seeing the projected motion of these blobs of this material, this wave-like material. So it is hard right now to sort out the dynamics. We're looking along the line of sight. But it is pretty clear from these measurements that at least some of the features are super Keplerian. That is, they seem to be moving faster than what you'd expect from just simple Keplerian rotation and are being pushed. I shouldn't say pushed, but are moving out of the system.
Okay.
You can't. So there's another hypothesis that's been put forth, and it's incredibly speculative, without any evidence really at this point. But you can imagine that if, for example, there might be a planet, when we don't know that there is, that would be orbiting close in. It is a much smaller star, and you may have planets orbiting closer in. And certainly from Kepler, we've seen all sorts of architectures of planetary systems. That when you have an ejection like Carol described, it's possible that there's enough energy there to strip material from around that planet, say from its atmosphere. And so we may be seeing some interaction between these very strong winds or material outflows, coronal mass ejections, and interior planets if they're there. So this is something we don't know. It's very speculative, but it could be happening in this system.
Okay, well this is amazing, and I've learned a lot about the system and this debris disk idea, as well as I'm hoping we get more observations coming from it. I want to get to some of the questions here. An old standby, one of our regulars, Andrew Planet, who said he couldn't make the hangout because he had to go to work, was asking. He left a question before he left, which was good. Thank you, Andrew, and I hope. That's why I'm getting to yours first. Is stellar birth and early formation analogous to fractional distillation, and that the higher elements of molecules get in that the higher elements? Let me start again. Is stellar birth and early formation analogous to fractional distillation in that the lighter elements or molecules get pushed further away? Does that make sense to you guys? So is in early formation of these things, is there something that pushes lighter elements out of the way and leave just the debris disks?
We haven't seen anything like that. There are a bunch of studies in progress to look at, trace amounts of gas in some of these debris disks, not AUMIC, but those have tended to show a range of elements and no evidence for preferential enrichment of heavy elements. Now, you have to understand that there are processes that will lock material in the solid phase. If you're far enough from the star, most of your volatiles will be ices, just as in our solar system. If you think of the icy moons of Jupiter and Saturn and beyond, and what we've seen with New Horizons of Pluto and its system, you also have rock-forming elements that typically are in the solid phase in these systems, and that actually forms a large component of the dust.
All right. Well, thank you, Andrew.
But we haven't seen anything like a distillation process.
Okay. Very good. Thank you. Go ahead, Emery.
Yes. If I may add something, comparing again Eumic and Beta Pictoris, and in the case of Beta Pictoris, which has also a debris disk, we see infall of gas going on the star. So there is gas, a little bit of gas around the star. In the case of Eumic, we don't have any evidence of gas around the star. So we cannot do any compositional analysis or so.
Good, thank you. Okay, Charles Astro is asking, could the fast-moving blobs in Eumic's disk be very large comets that have had a swing-by encounter with a giant planet and are now on an escape trajectory from the system? Any chance these are related to that? Comets or some kind of flyby? And I'll leave that to Anthony. You want to comment?
I have no answer.
Basically, the idea is you don't have any idea what these things are.
You also should remember that the size of the structures that we're seeing are large, up to 10 AU or so.
Yeah.
So these are big things.
Much bigger than a comet.
Way bigger.
And much bigger than the comets that we've seen in our system or that we think are important in the Beta Pictoris disk.
Okay.
The one thing I would like to point out is whatever the mechanism that is ejecting material, if it in fact is removing material from the system, it is dispersing the small grain debris, and maybe why it has proven to be so incredibly difficult to image debris disks around other and particularly older M stars.
Okay.
There are two, count them two, debris disks known around M stars, Eumic, and then the much older GJ581 system, and that was detected not with Hubble, but with Herschel, so sampling much larger grains.
Oh, I see. Okay, so that makes it much harder to view with these, or to observe
And,
with these.
those are the only two that have been found thus far, not for want of people looking.
Does that surprise you? Because you sound a little bit, surprised by that fact. Should you see more?
I don't think people had expected it, because all of the processes that we think are important in disks around much more luminous and hotter stars, like radiation pressure blowout. Think solar sailing dust. Just scooting on out there. Should not be operating in this system.
I see. Okay. Well,
because the star is not very luminous, except in terms of its flaring.
Okay. So
I have a question. Is this a debris disk and all this sounds pretty nasty for planets?
Well, there are people who are looking at what the habitable zone would be for stars as a function of the stellar radiation field, both the light and also particle radiation. And the concern with M stars is if you're stuck in a disk very close to a really active star, you better have a plan for a radiation shielding.
So you're talking about planets that are already in the debris disk, then, right, Carol?
Well, we know in the GJ581 system that there are multiple planets close in. They've been detected with radial velocity searches.
Well, I guess I don't see how you're going to have one without the other. I mean, if you've got these planets condensing out of these disks to begin with, at some point you're going to have kind of both at the same time. You're going to have a planet and a disk.
Sure. Let me can I respond quickly to Carol Christian's question or comment?
Maybe. Let me think about it. Sure. Go ahead.
Okay. All right, let me think about it.
Go ahead.
No, just a reminder to Carol, of course, that we sit in our own circumsolar debris disk right here in the Earth. The Sun has a debris system. It's much more tenuous than we're talking about with like Beta Pic or AU-MIC. But this is probably a common phenomenon around stars. There may be mass loss over time, and we may see less of a particle density. But we have our on various size scales. We have the Edgeworth-Kuiper belt, we have our main asteroid belt, and we have the zodiacal component of small grains in our own solar system. So and there's features. There's a resonant ring, for example, that trails the Earth in its orbit. So I wouldn't say it's a hostile environment. I sort of got that sense from your question. But planets and debris go hand in hand. There's no question.
I was going to say, I wondered how you could have one without the other. Okay,
well,
that's good.
You can
Thanks
have
for
one
clarifying.
without, but it sounds pretty nasty. So,
Yeah.
Well, the concern with planets is you can affect the close-in planets. You can affect the atmospheric chemistry, and you can affect whether you would want to spend any time on the planet's surface. In extreme cases, you might end up with a rock with no atmosphere.
Okay.
Hence,
Or very little atmosphere, which would certainly affect whether we would want to go there on vacation.
I would go anywhere on vacation outside the solar system if I could, regardless of the conditions, just because we could.
But people have been interested in this since M stars make up about 75% of the stars in our galaxy. And Kepler has certainly demonstrated that they have no problem having planets.
That's right. It's a very common occurrence, 1.6
So,
per
so the
star
question
in the sky.
Now, the other thing with M stars, if they start off with these very high levels of activity and it decays very slowly, then you're susceptible to very rare events. I mean, it might be something that you're seeing every decade, every 100 years, but you've got a lot of decades and 100 years to go.
Yeah. Well,
and so this is why people are interested in this in terms of the habitability of planets in these systems.
Because it could have a pretty important impact on that as well. That's a good point.
And who knows? Some life may think that this is just a nice bathing experience.
Well, I want to know myself just how common life would be in some of these debris. If it's microbes or bacteria or whatever it might be, would be a fascinating question to find out the answer to as well. But I want to follow up on Juan Borda on the Q&A app. I want to follow up on what Carol Grady was saying about this. Only two M-type stars have been known to have these debris disks. So he's asking, are there plans to increase the temporal resolution of this phenomenon, sort of increase the frame rate, as it were? So maybe Anne-Marie, you can comment on that. But are there any plans to say go back to look more at this thing in depth and get more frames in the movie? Anybody? Go ahead.
I see Anne-Marie is muted. I will say that we actually put in a proposal for Hubble time for next cycle to do that, which had not been accepted, but of course that was before the results were published. So we're going to ask again, and Anthony has put in a proposal to follow up more with Sphere. So we're hoping to definitely, we only have the 3 epochs, and the 2 Hubble epochs are very close together. There is one detail about looking at the Hubble and Sphere data together, and that is that they were taken at different wavelengths. Now that in no way should really affect the overall findings of this sort of super Keplerian motion of these features. But the detailed morphology of the features is going to be a little bit different at different wavelengths.
Well, I'm really glad you brought that up because I wanted to talk about the wavelength. So why don't you tell us what wavelength Hubble looked at, and then Anthony, maybe you could tell us about Sphere?
Sure. Hubble is broadband optical. It's basically unfiltered in the STIS instrument. Okay. So it's visible light is what you're seeing over a very wide part of the visible spectrum.
Okay. Yeah, Carol's or Anne-Marie's saying she can't hear. So yeah, if maybe she can come back out of the Hangout and come back in. It should fix it for her. Okay, Anthony, what about Sphere? Can you tell us a little bit about the wavelengths it observes then?
Sphere is working in near infrared mostly. So
of
this
course.
is
near infrared.
This is where the AO system, the adaptive optics, is most efficient, in fact.
Okay.
So and this is also more convenient for, in that case, to look at planets or debris disk. So yeah, I mean the instrument we used is a near infrared camera It's very just a simple camera with different filters, and we got only a sequence of about 1 hour on this target on AUMIC in 2014 in the infrared.
Okay.
So,
All right. Well, does that? So I'm going to follow up with you then on another question, Anthony. I'm not sure if it's someone else is better suited for that. Let me know. But Juan Board is asking another really good question. I think what are the materials and the temperatures of the disk? Now we've talked about what Carol Grady has mentioned something about the fine grain structure of the dust grains themselves. But what about the temperatures? How hot is? Do we know anything about that? Anything about the temperatures? And what do we mean by temperatures of a debris disk? Do we mean the temperatures of the radiation of the grains themselves, or the motion of the grains? What do we mean by the temperature?
Well, for sure, in the images we are not able to derive a temperature, so we do that by another way, like doing photometry at different wavelengths, and especially in far infrared. And in the far infrared, well, I don't remember exactly the temperature of AUMIC, but it should be something like a few tenths of Kelvin or something like that, because the main belt is at 40 AU from the star, so it's relatively far, especially for this star, which is much fainter than the sun. So it's something like that. Maybe Carol will know exactly the temperature. I don't know.
Do you have any comment on that, Carol? Carol Grady?
It's definitely cold, and people should think about it in terms of, we're talking about material at the same distance from AUMIC as Pluto is from our sun, and our sun is hotter. And small grains will be in thermal equilibrium with the radiation field that lights them up, and then they glow in the dark very efficiently.
Okay.
But they're cold. They're very cold.
Okay. Well, that's good. Thank you, Juan. That was a good question. John Glasgow is asking, what is the time frame for planet formation, if they form at all, from the present stage in this star's evolution? So from what we're looking at now, what do you think the time frame is for getting planets to form in a system like this?
Well, we think that Jovian mass planets, because they have massive gaseous atmospheres, formed earliest and form up to probably 5 to 10 million years, possibly a bit earlier in some systems.
Wow, that soon.
The age of AUMIC is currently estimated to be about 23 million years, but that's getting close to the point that in the history of our own solar system, largely derived from meteoritic data, that the Earth and Moon were starting to form. So we're on sort of the early end of the terrestrial planet formation epoch.
Okay, good. That's a good question, John. Thank you. So let's see. Astro Girl 1 USA is asking, how many debris disks has Hubble Space Telescope seen altogether? Now, I know that you've said there's only been 2 of this particular kind of star, but can you give us some idea of how many these things are around other stars?
That's a great question for Glenn.
Okay, Glenn.
Well, the number that Hubble has seen is really very heavily biased by the number that Hubble has looked at, I have to say.
That's with all things, yes. Observational bias.
Now, that said, the number slowly changes on timescales of months as people observe new disks, but it's on the order of 24. There's roughly 20 disks, circumstellar debris disks that are light scattering that have been observed with Hubble coronagraphy. So that's the number we're talking about, and that's approximately the number that have been seen, of course, because the ground is going after mostly the same set of disks at different wavelengths and using different capabilities. And so we're sort of in the 24 to 30 overall imaged debris disks in scattered light, which is the sort of sense of the question I'm getting, asking about what we've done with Hubble.
Right. Well, what about Sphere?
There are debris disks that have been spatially resolved with Herschel, and the estimates are for stars more massive than AUMIC, up through A stars, that it's about 20 to 25% of stars seem to have these debris structures around them.
20 to 25%.
That's an important number. I really wanted to stress that, with Hubble, it's sort of what we've looked at. We really think we're looking at the tip of an iceberg. These debris disks are probably fairly common in general, but they're very hard to detect, and Hubble gets the low-hanging fruit.
Well, that makes sense, though, doesn't it? I mean, Kepler's coming back with all these planets, 1.6 on average for every star in the sky. We would expect that, wouldn't we? To be able that these disks will be a pretty common occurrence, if there are so many planets around other stars.
Sure, at some level. We measure the dust content in kind of a proxy number called a ZODI. A ZODI is roughly equivalent, is equivalent to the amount of dust in our solar system. And the debris disks that we're actually imaging in scattered light are thousands of ZODI. So we're not down at the levels of anything like our solar system. We're in between. In fact, the WFIRST mission, which is a conception that we hope may someday fly, has a coronagraph that may actually get us down into the tens to hundreds of ZODI levels, tens if we're lucky. So we have a long way to go yet.
Okay, comment a little bit for us on Anthony about SPHERE. How about SPHERE? Is it finding this to be a pretty common?
Yeah, I think so. Especially we are just starting the observations this year. We started in February to do the regular observation, and what we can say is that we already have a few new disks. So this 24 of debris disks that Glenn has mentioned will probably grow in the next years, and both SPHERE and GPI will be very efficient to detect these disks.
Now, Anne-Marie, if I'm understanding right, thanks for joining us again. I guess I know you had some technical difficulties for a moment. It's good that you could make it back. As the name implies, exoplanet is in the name of the instrument acronym. So this was the kind of thing, right, that you had in mind with looking for these debris disks and planet formation mechanisms, correct? You're muted. I'm sorry. You need to unmute.
Unmute.
There you go. There you are. Now we
so
can hear you.
I'm not sure I got your question properly. What I can say is that we know that planets and debris disks are connected in some way. So in the search for planets and the search for debris disks is quite connected. This is why, as Anthony said, our program is mainly to look for planets, and in fact we find disks as well, just because we are a little bit more sensitive than we were before.
Can you give us some content on, or some context for how you're using SPHERE image? How does it do it? I mean, as I understand it, there are two main ways of finding exoplanets. There's the transit method, where we measure dips in brightness, and then there's the one with the wobble, the spectroscopic wobble, and for some reason the name is escaping me right now. But what is SPHERE designed to do? How is it designed to study exoplanets specifically?
The methods that you mentioned are indirect methods. In transit or in radial velocity, you don't search the light of the planet itself. You study the light of the star around which the planet is orbiting. So it is an indirect method. Here we are looking for direct photons coming from the planets themselves. So we do imaging like pictures of the planets. And this is the basis of our research, of our survey.
Wonderful. So that helps explain the coronagraph and the blocking of the star's light, but it's critical to be able to image these planets directly, and you, of course, are using it, in this case, for AUMIC for the debris disk itself. So that's really cool. All right, well, thank you, Astro Girl 1. That was a good question. I appreciate that. Let me go see what else I've got. And Musical Image is asking, is it plausible that the star may have higher fluctuations of stable gravitational, electromagnetic, and or CME activities during the unusual debris coagulation? So could, I guess the question, as I understand this question, could the debris disk be driving some of the activity of the star?
Well, most of the debris, certainly the features that we are imaging, are at Saturn's, the equivalent of Saturn's distance from AUMIC and beyond. So it is hard to see how there's going to be a back reaction on the star. One possibility is we see these sort of arc-like features, and that may just be material that has been snow-plowed up. If you think of it, something that's spherical or quasi-spherical, as many people think a coronal mass ejection might be, the plasmoid might be. It's going to go through a disk and push things out of the way, and it acts essentially like a snowplow.
All right, awesome. So thank you
So
for.
what we may be seeing is the interaction of material in the disk with the space weather of the system.
Right, and that's, yeah, we alluded to that a little bit earlier on, and space weather is a very interesting topic too to go into, is with both not just the sun but other stars as well. Okay, well we're running out of time, so I need to stop it there. I want to thank everybody who asked questions. Thank you all very much. I want to thank our guests Anthony Bocoletti, Anne-Marie Lagrange, Glenn Schneider, and Carol Grady for joining us. Their paper, which the results we've just been talking about, came out today in the British journal Nature. So I don't know if you guys can get that online or not, but I would encourage you, if you're interested, to delve in a little bit deeper. And I want to thank all of you for appearing in our Hangout. Thank you so much. This has been a lot of fun. Really appreciate it.
Yeah, it was great. Thank you very much for your time. And I'm glad everybody who was really busy, which is all of you, could make it.
As always, I know everybody taking out time for your busy schedule to share
really
with us what you found. Really do appreciate it. Next week, folks, we're going to be talking about Jupiter. Hubble has been looking at Jupiter again, and we've got a hangout looking and devoted to all Jupiter all the time next week. So we hope you'll join us. Until that time, on behalf of Carol, I want to thank you guys for watching. And as always, keep
looking up.
Here that are of common origin in terms of where and when they formed. Beta Pictoris, of course, is famous for its very large and well-known disk that was discovered in 1985. AU Mic is sort of its baby cousin, you may want to say. It's a smaller disk, but it's a very bright one and very massive one. The disk was first seen in 2003, I think, by Paul Callis. I may be wrong about that. I think it was identified on the ground, actually. I apologize, by Michael Liu. But the disk has been known for some time. We observed it last year. Excuse me, we reported it last year, but we observed it in 2010 and 2011 with Hubble, and Anthony now has done observations with Sphere that we'll talk about. So it was the follow-up that Anthony did, then going back and looking at our observations again, that really formed the collaboration between what we were doing with the Sphere group. The Hubble data that we took, and I don't want to get too much into the data here, they were taken in two epochs fairly close together in time, and we treated them as one coherent data set, but it's actually very interesting when you start breaking apart sort of the time resolution, especially the time baseline that Sphere gave us, or as Anthony did. They went back in 2014, looking at it many years, 3 to 4 years later. So we're able to see some
Hello, Hubble huggers, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and we have another really interesting hangout planned for you this week. Astronomers using NASA's Hubble Space Telescope and the European Southern Observatory's Very Large Telescope in Chile have discovered a never-before-seen moving features within a dusty disk surrounding the young, nearby star known as AU Microscopy, or affectionately known as AU Mic. And we're going to be talking today about some of the findings of these observations with the astronomers who made them. But before I get started, let me let you know that we want your comments and your questions throughout the Hangout. And there's several ways you can let us know how to do that. The easiest way is to use the Q&A app. There's a little button on the lower left-hand corner of your screen called Q&A. You push that, and you can ask a question. I've already seen a whole bunch of them right here, and I'm going to be getting to them as we go along. And feel free to also do your comments as well. We're also monitoring the Hubble Hangout hashtag, just Hubble Hangout, not the hashtag part, and on Twitter. So I'm looking at that. I won't be live tweeting this.
He's from Grenoble.
Exactly, Grenoble.
Yeah, so you can see why I wasn't going to do that, right, folks? If I had done that, you would have been like, "What's he saying? Oh my God, he really butchered that." So okay, so our team here today has used the Hubble telescope and another observatory known as Sphere in part of the Very Large Telescope that runs by the European Southern Observatory in Chile to look at a nearby a nearby star known as AUMIC, and it is about 32 light years in the constellation Microscopium. And I'd like to get, I guess, who can give us some background on this? Glenn, would that be something I could get you to give us some background on the star system itself? What kind of star is it, and things like that? And
sure, happy to. Yeah.
Mm-hmm.
Yeah, so AUMIC is a relatively young star. It's between about 10 and 20 million years old. It's visible in the southern hemisphere. It's about 32 light years away. It's a very low-mass star, what we call an M spectral type star. It's about 30% the mass of the Sun or so.
Oh, wow, really? So it's pretty small.
It is. It's red, it's cool. It's about 3,500 degrees Kelvin, more or less, surface temperature. And it is a very active star, very chromospherically active.
This particular one, but we will be looking for that hangout also on the G Plus event page. If you want to leave comments there, there's plenty of ways to do it. We hope you'll ask our guests lots of questions. But before I get started with my introductions, let me welcome my colleague and friend, Dr. Carol Christian. She is the
hello.
Hi, Carol. She's the outreach scientist for the Hubble Space Telescope. How are you doing?
I'm doing well.
Yeah, you're doing really good. So
I escaped the floods of the South, so I
wanted to ask you about that. I know you were heading that way. I heard.
Anyway, we made it.
That's great. Well, welcome. It's good to have you back, and looking forward to a good conversation here today. With me today is Dr. Glenn Schneider. He's an astronomer at the University of Arizona. Also joining me is Dr. Carol Grady. She is an astronomer with Eureka Scientific. Sorry, I couldn't read my writing there for a minute.
Eureka Scientific.
She's based at Goddard. Welcome, Carol. It's good to have you. Also joining me is Anne-Marie Lagrange. She's a researcher, and I'm going to let her tell you from where in just a minute. And also joining me is Dr. Anthony Boccaletti. He's from Paris Observatory, also an astronomer. Welcome, folks. I'm glad you guys could all join us.
It has lots of flaring events and rather violent events. What we call mass ejections from the surface, chromosphere.
Now our sun actually does that too, right? I mean,
it does. And it absolutely does, but not with the frequency and not with the energy relative to the size and energy of an M star. So these are some, I won't say catastrophic, but they're very energetic events for a small star.
So for those of you who don't know, the chromosphere is this sort of layer of a solar atmosphere, or stellar atmosphere, I guess, in this sense. It's above what's called the photosphere, which is what, on our sun at least, is where things like sunspots or where those are seen in the optical wavelengths. But then it's a layer right above that, a little bit higher up, but it's in between that and the corona. Am I right?
That's exactly right.
Okay, so it's this very special region of AUMIC that you were looking at.
Well, it's not that we were looking at the region. It's just the chromospheric activity is a marker of the activity in the star itself. So we know
I see.
It's a very active star.
I see. It's just a characteristic of its activity. I see. And wow, that's interesting. I'd like to talk more about that in a little bit. But so this star's pretty close by. And what was the motivation for looking at this particular system?
So AUMIC is actually a member of the Beta Pictoris moving group. There's an association of stars in the southern hemisphere.